joining us. This is our second annual Vagelos Institute Lecture in Energy, part of Energy Week, a full week of energy-focused events on the Penn campus. And it's put together by the Kleinman Center for Energy Policy, whose great space we are in right now, and the Vagelos Institute for Energy Science and Technology, and many other partners across campus. For those of you who don't know me, I'm Karen Goldberg, the director of the Vagelos Institute for Energy Science and Technology. And I'm also the Vagelos Professor in Energy Research and Professor of Chemistry at Penn. I am thrilled to introduce our lecturer this year, Professor Jenny Yang from the University of California, Irvine. Dr. Yang's research program has focused on developing the fundamental understanding that's needed to create viable catalytic systems for the production of liquid fuels and feedstock chemicals using renewable energy. Water splitting and carbon dioxide conversion to fuels have been key targets in the Yang group. And through her lectures today and tomorrow, we will see why these are so important and how our group is using synthesis, electrochemistry, and spectroscopy to design, optimize, and develop these new catalysts. Professor Yang is also working on the very important problem of efficiently capturing carbon dioxide from the air for utilization or sequestration. And she and her team have very exciting results in that area as well. I note that her interests in renewable energy and sustainability date back to her undergraduate days, where she actually did an internship at the National Renewable Energy Lab, so NREL, where she was an undergraduate. So that probably has something in common with our Viper students who are getting inspired about energy and sustainability through your undergraduate research. Dr. Yang received her BS in chemistry from UC Berkeley, where she did undergraduate research with Jeff Long. She then got her PhD in chemistry working with Dan Nocera at MIT. From there, she traveled to Washington State, where she was a postdoctoral associate and research scientist at the Pacific Northwest National Laboratory, PNNL, in the Center for Molecular Electrocatalysis. After a few years at PNNL, she worked briefly at the Joint Center for Artificial Photosynthesis, the first solar hub, so this was JCAP, at Caltech before starting as assistant professor at UC Irvine in 2013. She was then promoted to associate professor in 2019 and then professor and chancellor's fellow in 2021. She has received numerous awards for outstanding research, including an NSF Career Award, a DOE Early Career Award, a Presidential Early Career Award for Scientists and Engineers, PCAS Award, the American Chemical Society Inorganic Chemistry Lectureship, a Camille and Henry Dreyfus Teacher Scholar Award, a Sloan Fellowship, the Chancellor's Award for Excellence in Fostering Undergraduate Research at Irvine, and she's actually currently the director of the new DOE-funded Center for Closing the Carbon Cycle, 4C, which is a new DOE Energy Frontier Research Center. So we're delighted to have you here. We're so excited to hear what you have to say, and welcome to Energy Week at Penn.
Thank you so much for that introduction. Karen, you're absolutely right. It was my undergraduate research that got me really excited about sustainability and energy. Once I did that internship at NREL that summer, I was like, this is what I want to do with the rest of my life. I want to be able to use science to try to develop technology and understand things better to improve our sustainability and improve our technologies in that respect. So that is absolutely correct. This here a little bit. Okay, everything ready? Okay. So the talk today, I'm going to give you sort of the motivation for some of our research program and some of the things that we learn about it. It's called Inspired by Nature, Understanding the Chemistry That Powers Our Planet. How do we power ourselves? How did you guys get here today? What gave you the energy to do that? To get up in the morning, come to campus, come here? You guys probably had breakfast, maybe lunch now. Okay, so we definitely, coffee also, but really what we need to power ourselves are things like food, what we eat for breakfast and for lunch and for dinner. If we didn't do that, we wouldn't have any energy to power ourselves. So the second question I have for you is, how do we power human civilization right now, for the most part, or historically over the last few decades, century or so? Fossil fuels, right? So we basically use fossil fuels right now to power most of our human civilization. And that is a problem because we can look at the data that's been taken at the Mauna Loa Observatory on CO2 levels in the atmosphere over the last 50 or 60 years or so, and we know that that level is rising. And the reason why that level is rising is because our use of fossil fuels is basically combustion, right, with oxygen and heat to basically make energy, which is the part that we want, some water and CO2. This is the chemical reaction that we use in order to, when we use fossil fuels for energy. And so right now, we're looking at global terawatts of energy. This is our burn rate for human civilization, about 18.5 terawatts in 2015, and it's projected by 2030, it's kind of hard to see in yellow there, 28 terawatts, and then by 2050, about 50 terawatts of energy is what's going to take to power our planet. And if you think about the resources available for us to do that, this is our world energy consumption that's shown here. And in 2019, it was 23 terawatts. If we think about total reserves on the left side, these are basically things that are, the total amount that's believed to be available for us to use as energy. There's about 830 terawatts of coal, so there's a pretty large resource that's available. There's uranium that we can use in nuclear as well. This is not a renewable resource, but it's a resource that we have a lot of that's available on this planet. Not all of it's easily accessible, but it's there. There's oil, about 335 terawatt years of oil, and then there's about 220 terawatt years of natural gas. So there actually is a large abundance of non-renewable sources that we have at our disposal to power our planet. But there's also renewable sources as well, things that are basically, we can count on an annual basis of what's available for us to use. So there's tidal and wave, right? These are fairly small. This is basically using wave energy, which is effectively lunar energy to generate electricity. We can use hydro. This is not our current capacity, but this is sort of like a max reasonable capacity. If we dam a lot of rivers and streams. There's geothermal, which is also available. It tends to be very geographically, limited in its use. There's biomass. This is what's believed to be available at this time, given the amount of arable land that we have resources. And then there's wind, and this is again the total amount of capacity that's believed to be available if we took advantage of it. So I'm missing a big one here for annual resources. Can you guys guess what that is? Solar, yes, right. So solar is 23,000 terawatts, and if we put it on the same map, you can see that there's a large abundance of solar that's available to us. You may have heard the statistic before that enough sunlight hits the planet in 1 hour to power human civilization for 1 year, right? So it's a very, very abundant resource that's available, that's renewable, and doesn't require fossil. The amount of photovoltaics has been growing globally. You can see that a lot of it started in Europe. If you look at more newer numbers, and China is taking a larger share of photovoltaic installations. And as the installations have increased, the cost has gone down. So this is the cost of solar electricity from the 70s to more recent times. Many of you guys have heard of the Moore's law with circuits, doubling the capacity every 10 years. The Swanson effect basically says that for every doubling of output of solar, then the price goes down by about half, and that's basically happened every 10 years, except it's accelerated more recently. So the number there, the number from look at my screen here because it's hard to see, from 1977 it was about $76 a watt. And then in 2013, it was about 74 cents a watt. So you can see that it's gone down by a tremendous amount. And recently, when I looked this morning, it's about 18 cents a watt. So actually that decrease is accelerating as more installations are put forth, and we're able to generate more capacity for photovoltaics. So we know that the installation is increasing, the cost is going down. All of these are moving in the right direction for us to take advantage of solar energy as a resource for us. But what is the problem with that? Well, this is great. We have solar panels on your roof. I have solar panels on my roof, and during the day I can, it powers my fridge and I can work on my computer. I can watch TV. But one problem with that, which doesn't happen a lot in Southern California, is that it could get cloudy, right? And then the solar generation will go down. But again, in California, it's not such a big issue. We have a lot of sunny days. So what's another issue that you can think of that might be a problem for using solar energy to power your home? Nighttime. That is the biggest problem. And it's the biggest cycle is that the sun goes down every night and we would still like our refrigerators to work. We would still like to watch TV and we would still like to work on our computers and have lights on at night. But there's no solar generated at that time. And this is a very big problem in California. There was a lot of solar capacity that's been installed over the last 10 years. And then 2017, for the first time, in the middle of the day, the amount of solar generated exceeded the use. And at that time, they basically paid Nevada and Arizona to take that excess electricity to stabilize the grid, right? So we're basically giving away solar electricity for free, but then we have no capacity of getting that back when we need it at night. And this has actually become an increasing problem in California. What they do now, instead of paying other states to take it, is they do what's called curtailment, which is they basically don't accept solar or wind anymore. The panels are sitting out there doing nothing. And this is actually, I think they said last April, there was enough solar and wind curtail that it was equivalent to 2 months of electricity generation at the Hoover Dam, right? So it's a large amount and it's growing. As you can see from this map, it tends to be, the spring tends to have the largest amount of overgeneration. We get nice long sunny days. The weather's so cool, so people aren't using the air conditioners. And so this is becoming an increasing issue in California and many other areas that have installed solar. I think Germany, which was one of the early adopters for putting in a lot of solar, they basically sell some to Switzerland, which pump the water uphill for their hydroelectric dams, right? Which they can then use later as well. And then there's another question too, is that how do we use solar to power transportation, right? So long haul trucking, airplanes. There are a lot of places where it's not really practical to put a solar panel on there. You wouldn't be able to generate enough energy to drive any of these things. So when I first gave a public talk about 7 years ago, there was this really great article that had come out in Forbes. This is why energy storage may be the most important technology in the world right now, right? Because the point is that most renewable sources that we want to use are intermittent. They're generated not when we need them, and then we would like to basically save them for the actual rainy day, not the metaphorical rainy day, so that we can use it or at nighttime or seasonal because we generate a lot more in the summer than we do in the winter. And then just recently, Forbes still said last year in an article, we have an energy storage problem, right? And this is something that needs to be solved. So, when we think about energy storage, we often think about batteries first, because that's probably what we're most used to when we think about having something in our pocket that stores energy. So Edison and Tesla paired up to make a giant energy storage system. This is about an hour from my house in Mira Loma substation, and that happened a couple years ago. And they've done similar things. There are power walls that are sold, which you can put in your house that can basically store energy during the day to be used overnight. And this actually is nice because it gives you a little bit more off the grid flexibility in the case of rolling blackouts or other issues. And then a lot of solar systems like this one in Kauai are now, when they're built, these solar farms are coupled to energy storage mechanisms so that they can basically deal with this daily problem. But at this point, they're basically not enough to satisfy a complete conversion to solar or wind or other types of intermittent energy. So we think about energy storage. Probably one of the very important factors, especially for things like transportation, is density by volume and density by weight. And of course, as I said, we always think of batteries often first when we think about storage because that's what we use in our cell phones and our computers. And if you look at this graph, energy density on the y-axis by volume and by weight in the x-axis, you can see that lithium batteries, other acid batteries are not really that good. And you can argue that maybe I just drew my axis to make them look terrible, which is not true because there are things that are much better. And these are the things that we use all the time when we think about moving energy around in large quantities, right? In airplanes and in cars, is that we basically use chemical energy, which is energy stored in the form of CC or CH bonds. And these are super energy dense compared to something like a battery. And so you can see here, like diesel, gasoline, all these are things that we use regularly in our fossil fuel infrastructure. And so the question is, can we use sunlight to form similar types of energy dense bonds? Can we use them directly to basically form chemical energy in the same fashion? And this actually already goes on right now. Does anyone want to guess what that is? Yes, thank you. Photosynthesis, right? So this happens every day all around us. Photosynthesis does exactly that. It basically turns solar energy into chemical energy, into CCCH bonds. And so this is sort of the net equation for that. You know, you take CO2 from the air, some water and sunlight, and then you get fuel. And then you get O2 out as a byproduct of that, which is of course very convenient for us because we need that O2. And so if we think about the scale of this, it's 130 terawatts a year is natural photosynthesis. It's in the tens of gigatons of CO2 that is fixed through natural photosynthesis. And one thing I always think is very interesting is that, you know, ever since I was interested in energy and CO2 research, I've been, you know, looking at this Keeling curve is what it's called with the CO2 level. And one thing I didn't notice for a long time, but if you see here, is that it keeps going up and down, right? And it wasn't until actually an atmospheric chemist explained it to me, which is that when it's spring and summer and photosynthesis is more active, actually global CO2 levels go down. And then when it's winter, they go up again. And I was like, well, okay, that's cool, but like this northern southern hemisphere are opposite cycles. How does that work? And it turns out that, you know, most photosynthesis happens on land and most of the land mass is in the northern hemisphere. So when the northern hemisphere is having spring and summer, global CO2 levels drop. And then in winter, they raise again as photosynthesis is less active. And so I always think of this now that I've noticed it and someone explained it to me, that it's like the earth breathing, right, every year on an annual cycle as the CO2 levels go up and down. But of course, they are going up as a net thing. So if we go back to ourselves, is how do we power ourselves? If you really think about where every single calorie that we eat and every single food that we eat, they all came from photosynthesis, right? We either eat plants directly, we eat animals that eat plants, you know, everything that we've ever had, you know, milk from cows, anything like that, we're all solar powered, right? All the energy that powers us came from the sun as well. So the question is, so just to sort of put that in the natural context, if I go back to this graph and I put a lot of natural chemicals that are formed through photosynthesis or other means, metabolism, you can see that, you know, vegetable oil is sort of comparable to something like gasoline or diesel, body fat, obviously a fantastic way of storing energy, whether we like it or not. Sugars, glucose, wood, you know, these types of biomasses as well. And what I always think is very remarkable about that is that if you think about transportation as being an area where energy density by weight and volume really matter, and we think about airplanes, you know, I can take an airplane from LAX to Sydney, Australia, 7,000 miles, no refueling. It is kind of a miracle, right? If you think about, you know, the energy it takes to power a plane to go 7,000 miles, you have to carry your weight with you. So it has to be very, very dense as well. And then nature actually does exactly the same thing. This is a bar-tailed godwit, which is a bird that also does a 7,000 mile migration over the Pacific, does not stop once. There's no place for it to stop and eat, and basically loses, you know, more than half its body weight, which is body fat when it starts. And it's the same thing where, you know, we use jet fuel for planes, you know, nature uses body fat, right, as a way of basically making a really fantastic transportation fuel that can, you know, get places far with, you know, packs a punch basically by weight and by volume. Okay, so the natural way of doing photosynthesis is sort of shown here, where sunlight hits a leaf and then basically separates it into protons and electrons. Half the reaction is basically taking water to oxygen, and then the protons and electrons that are released from that can be used to reduce CO2 into different kinds of fuels. The area of artificial photosynthesis is trying to replicate that process using things that we synthesize and that we make. And so, you know, we know how to collect solar energy through the use of photovoltaics that separates, you know, protons, electrons and holes, and that basically can use to drive an electrolysis cell or an electrochemical potential. It's like a backwards battery to basically run exactly those reactions, right? So on one side, we can take take water and oxidize it to oxygen, and then the protons and electrons that balance that reaction out could be used either directly to make hydrogen gas, which is a chemical fuel, or it can reduce CO2 into more complex things. So this area of chemistry is often, the fuels that basically result from this are often called solar fuels. Hydrogen obviously is a carbon neutral fuel, especially if you generate in this way, instead of from methane, which is more common right now. But also if we get carbon-based fuels using an artificial photosynthetic scheme, then they're also carbon neutral, right? Because you start with CO2 and when it's burned, that CO2 comes back out again, but it's not carbon that's from the ground. And that's the big difference there. Okay, so these chemical reactions require catalysts. And so a lot of people that work in this area, including myself, are really worried about how do we catalyze these reactions. So if you think about what catalysts do, basically, if you have the starting materials for making hydrogen, which is 2 protons and 2 electrons, it's a very simple reaction. It's one of the simplest reactions. You can put those together to make an H2 molecule that you can then use as a fuel. Uncatalyzed reactions have what's called a high barrier to them, which basically means that it takes a lot of energy to basically get over that in order to get to the product. And when we catalyze the reaction, we basically lower that barrier. We basically lower the energy it takes to get from point A to point B. And it speeds the reaction up. And so as it turns out, we already know how to take solar electricity and turn it into hydrogen fuel. So this is a polymer electrolyte membrane electrolyzer. I think it's been around since about the 70s. And you can see here that sunlight is hitting the solar panel at the top. And then on the bottom right, water is coming in. And it basically goes and it gets split. And on one side, on the anodic side, it basically, the oxygens combine to make O2. And then the protons and electrons go to make hydrogen on the cathodic side. And so, like I said, this has been around for a couple decades. And so you might ask the question, we already know how to do this. Then what are we doing? Like, why are we curtailing? Why are we, paying other people to take our energy? Why don't we just do this and make some clean hydrogen gas that we can burn later at night? And the reason why we don't, this is not, even though this is known technology, but it's not widespread, is because it's very expensive, right? So if we look at these reactions that are happening, on one side, it's water oxidation to O2. The other side is proton reduction to H2. The catalyst that's very commonly used for this water oxidation catalyst is iridium, right? So if you're not a chemist, iridium is actually not used for jewelry. It's very, very rare. It's only on our planet from meteorites, basically. So it's a very, very, very rare element. It's about $970 per ounce. And if you think about what we often use on the proton reduction side, especially in these types of electrolyzers, it's almost always platinum, right? And platinum, I have a platinum wedding ring, like it's used because it's in a very expensive, it's a precious metal that's often used for jewelry, but also used as a catalyst. And it's also similarly priced. It's very, very expensive. And the reason why I was always really fascinated by this is not like we don't know how to do it. We just don't know how to do it cheaply. And the reason why I was very interested in that is if you think about how nature does it, it does not use iridium and platinum to do its chemistry. It can't. There isn't enough of it available to actually run these reactions. And so we think about what nature uses. This is the photosystem 2. And if we look at where all the action happens, which is actually where water is oxidized to O2, this is the oxygen evolving complex, right? So this is the inorganic complex where the catalysis occurs. And if we look at what it's composed of, which I know is a little bit hard to see, you basically have calcium, which is very cheap, and you have manganese, which is also very cheap. And what I tell my group is that nature has to use dirt cheap metals because they literally have to use dirt, right, in order to get the things that they need to do the catalysis that they want to do. On the other side, if we think about what does the best proton reduction in nature, it's not in photosynthesis because they don't make hydrogen. They use hydrogenase enzymes are very well known for doing this reaction. And if we look at the active side of that, it's basically iron, right? It's not platinum, and it's very, very, very cheap. It's less than, it's actually very hard to do that calculation of how much it costs because they give it to you by dollars per ton or something, and then you get this very small number per ounce. So one of the questions that my group often asks is what lessons can we learn from nature so that we can make better catalysts composed of abundant metals that are cheaper than what we have now. So one lesson that we learn is about leveling the energy landscape. And so one thing that nature does is that you can catalyze the reaction by sort of having many highs and lows, as I've drawn here. But probably what's more important is to sort of level that out because you don't want highs and lows. As you go through a catalytic cycle, it's very energetically inefficient and it slows everything down, which is not a good thing when you want something to work well. And so one thing that my group does quite a bit of is really understanding the energy of bond making and breaking interactions. And so this is sometimes called thermochemistry, but if we look at this reaction, one of the early things that we did was we discovered this nickel catalyst, basically by leveling that energy landscape that can turn electricity, that can basically use electricity to turn water into hydrogen. We're only talking about the reductive side here, the cathodic side. And it functions at pH 1, which is actually pretty important because of the membrane materials that are currently available to us. It was very, very stable. And then we were basically able to do this by understanding each of those bond making and breaking events and making sure that we sort of keep them on an even keel and make sure that we're not doing highs and lows as we walk through our catalytic cycle. And that's something that we've basically applied to a lot of different catalyst development in our own lab. Another important issue when we think about catalyst design is proton management. So, when we think about doing this chemistry, we often always think about the electrons because they're the ones that are, oxidizing and reducing in their movement. But protons are always involved as well. And if you compare the two, electrons are super light and fast. They usually don't hold up reactions, but protons do. Protons are slow, they're very heavy, and they tend to be more sluggish, and so they end up being often a rate barrier in a lot of the chemistry that we do. And so the comparison I like to make is that, if electron weight is a bottle of water, a proton's like a car, right? So it's very different. Although I'm in Orange County, so we'll have a fancy car. Those are what my neighbors drive, not me. But if you watch the OC, you would know anyway. It's a very unusual place. But yeah, but it's like basically having to move something like that versus a bottle of water. And so when we think about our energy landscape again, and we need to move a car from one point to the other, what's the best way to do that? Well, we build a road for the car, right? And if we build a road, it's a lot easier to move that proton around as we go through catalysis. And so this is again something that we can learn from nature. So this is again the oxygen evolving complex, which is in photosystem 2. And now if you look a little closely, you can see a lot of dashed red lines here. And these dashed red lines that are shown here are hydrogen bonds. And basically hydrogen bonding networks allow us to move protons with lower energy from one place to another, and that we can replicate this in synthetic systems as well. So here's another molecule that we made in our lab. It's actually one of my favorite molecules because it just worked out very nicely. And it's basically a cobalt compound that has 2 waters bound to the cobalt. And then you can see here with these dashed red lines that they can make hydrogen bonds to these amine groups that are located off the ligand, right? So these are like weak interactions that can basically help move protons around within the molecule. I can show you a little picture of it. So that the gold ball in the middle is the cobalt, and then the red and white is the water, so it's H2O. And then each one of those is perfectly positioned to hydrogen bond with one of the nitrogens. And we can see that interaction in the structure where everything's distorted because of that bond exists. And that helps basically transport protons from water as the complex is being oxidized. So we were able to see water oxidation activity with this compound. We don't have the roads there. We don't have the amines there. We see no activity at all. So it's very important to couple that, that transport. What are other ways that we can use to move protons around? Again, we can look to nature. So this is the active site of that iron hydrogenase that I showed earlier that makes hydrogen, also oxidizes it in nature. And you can see here with this nitrogen that's here at the top, it's sort of perfectly positioned to help hand off hand off protons to the metal center or take them from the metal center. And then that is responsible for a lot of its really high activity in performing this reaction. And so we also can make synthetic mimics that basically replicate that type of interaction, right? So you have, this is a synthetic compound on the, this is a synthetic compound on the bottom. And you can see here that there is a replica of that sort of nitrogen that's poised over the active site, and it's sort of there to be perfectly positioned to deliver protons or accept protons as the reaction's happening. And so there's a lot of things we can learn from nature about how to basically catalyze these reactions very efficiently. And then the last lesson I'll talk to you, which is a little bit newer in my group, is how do we recycle CO2 into fuels? So CO2 is actually I've mostly talked about hydrogen and oxygen so far, But CO2 reduction is also a very nice way to access fuels that are very energy dense. But CO2 itself is very unreactive. So the half-life of CO2 in our atmosphere is about 800 years. So one of the real problems with reducing CO2 or turning it into fuels is that we have to activate that. And again, we look to nature. The way that nature does this reaction is it basically has this active site. This is the carbon monoxide dehydrogenase active site. It's composed of nickel and iron. And you can see here that the nickel and iron basically cooperate to bind the CO2. So it's basically, instead of having one center trying to grab and activate CO2, you have two, and that combined effort is better at basically activating that under milder conditions, under lower potentials. So we basically replicate that in a synthetic system again. So on the left, I'm just showing you what that looks like in a synthetic system. You have two things that can both grab onto CO2 at the same time in this cooperative fashion. And on the right side, we have a synthetic compound. It's a nickel barium compound that is also positioned to grab CO2. And so this is some pretty recent result from my lab, but this compound on the right can activate CO2 at very mild potentials, basically. You don't need to basically hit it with a hammer in order to activate CO2. You can do it much more gently, which is what we want to do if we want to do this reaction efficiently. So the lesson is cooperativity is key for CO2 activation. And then the bottom is, some people might ask, why are you making carbon monoxide? That's like poisonous. I have a carbon monoxide detector in my house. Carbon dioxide is actually quite energy rich. It is a gas, but we do know how to combine that with hydrogen at this point to basically make diesel fuel. This is a process that's been known for several decades, a Fischer-Tropsch process. So we can combine hydrogen made from renewable energy and CO made from renewable energy to get to more complex products in that way. Okay, so I'm just going to spend the last few minutes, and I only have a few slides on this, talking about carbon capture. As Karen mentioned, that this is an area that we've gotten into recently, and it sort of is based on the fact that I realized that we do need to actually have better ways of capturing carbon if we want to, one, recycle it or use it, but two, we have so much legacy carbon in the atmosphere that in order to get back to pre-industrial levels, that we'll have to capture some of it and sequester it as well. I can tell you a little bit about how we do it now. And this is the technology that's currently used with, I put clean coal in quotes there, and I'll explain why, that we use for capturing it from flue gas. So basically, we have absorbers that can bind CO2. So this is the exhaust from a fossil fuel plant. Sometimes it's usually called flue gas. And it binds to those capture agents. And then it basically gets heated to separate the CO2 in a concentrated stream. So here it enters dilute. It selectively binds CO2 from those dilute concentrations. And then when it's heated, it separates out CO2 in a much more concentrated form. And then the binder is basically regenerated and it can go and capture more CO2. So this is a thermal cycle since it uses heat, basically temperature swings to bind and release. And the theoretical efficiency is about 50%. And that's basically on Carnot limitations. The reality is it's actually much worse. It's about 3 to 5% for current amine methods. And there's various reasons for that. They can't swing to a very high temperature, just various issues with actual efficiency. But one of the things that many environmentalists and others are opposed to clean coal is that if you want to capture CO2 from, for example, a ton of coal, you have to burn an extra quarter ton to a third of a ton of coal to generate the energy to capture it from the first ton of coal. So you guys end up burning a lot more fossil, which is not very efficient, and you lose a lot of overall efficiency from your plant if you're capturing the CO2. We're an electrochemistry group, and so one of the things that we wanted to try to do is to use electricity to capture and concentrate CO2. As electrochemists, I always think electrochemical methods are better than thermal methods anyway. But one of the reasons for that is that you don't have these Carnot limitations that you have with thermal swings. You can approach 100% efficiency with an electrochemical system if you have the right molecules and the right things that are involved. And so I just want to show you a little bit of how this works. You would have a molecule that exists in two oxidation states here. And in one oxidation state, this is R-, it has a very high binding constant for selective CO2 binding. So you can put in a dilute stream here. It will capture that CO2, the CO2 depleted stream leaves. So everything else is very similar to what you would see in that thermal cycle, except here, instead of using heat to regenerate your sorbent, you basically you take away that electron. And now the CO2 no longer has an affinity to your sorbent. So then it comes out in a concentrated stream. That sorbent is then, of course, regenerated, and you can activate it again by adding an electron to it, where it can be recycled again. So there are molecules that are known to do this, even from concentrations that are relevant to air capture. But one of the problems when we started working on this was that most of the methods were unstable to oxygen. And that's a problem because there's like no application for CO2 capture that doesn't have oxygen present. So it's not useful if you can't, if it's oxygen sensitive. So I'll just talk to you about one recent result from our group in this area. We use molecules that are called quinones. These are simple organic molecules that are also formed naturally by trees in nature. And if you reduce them by 2 electrons, they have a very high affinity for CO2. That was already known before we started our work. The one thing that we did that was different was that we added these hydrogen bond donors in order to get these capture agents to have the properties that we wanted. And that was something that was new in this area. And you can see here that because of that, we were actually able to capture the presence of oxygen. So we basically imparted properties on this to make it more oxygen stable. And then what's shown here on this graph is that in black, this is basically passing charge, oxidizing the compound in order to release CO2. So you can see CO2 was initially captured. In blue dots is the CO2 concentration in the headspace. And then as we reduce the compound again, it starts to capture that CO2 again. So basically we can cycle back and forth between giving charge and taking it back, and then the CO2 is captured and released on cycle. This is one of the first examples of oxygen stable electrochemical capture using a redox carrier. Based on our lab metrics, which are admittedly very far from an actual metric in an actual proof of concept, but based on our lab metrics, it's about twice as efficient as alkylamine thermal capture, which is sort of the state of the art. Of course, we need to do a lot more to figure out what the actual efficiencies are if we scale it. And the other thing I really like about it is that both of the compounds that we use to do this, which is ethanol and this quinone, are both commercially available and super cheap. There are actually no metals in there either, which actually does make them a little bit cheaper as well. So I talked to you a little bit about some of the work that my group is doing this. I just want to point out that the things I talk about are not the only solution. There are many, many, many routes to decarbonization and sustainability. And I think it will take a lot of these different routes in order to achieve carbon neutrality. So, you know, there's a lot of work on harnessing renewable energy sources, different kinds of sources, including biomass. It's electrification. There's a lot of technology that needs to be done in order to electrify a lot of our current systems. Energy storage, there's been amazing developments in battery storage in the last decade, which I'm always in awe of. You know, I don't mean to rag on batteries, but they've actually made really amazing strides. Energy justice is something that's really, really important as we transition to a carbon neutral future. It's basically making sure that these gains are shared by all communities and that they're involved in the conversation as we change our infrastructure. That's something I think that is really critical. CO2 capture and sequestration. I'm not an expert on sequestration, but we do capture, utilization as well, and then also just decarbonizing a lot of traditional industries that are currently not decarbonized, especially the chemical industry as well. I'm a chemist, so we think about things like that. I want to thank my group who actually do all the work. So I have a really fantastic group of students and postdocs, undergraduate researchers as well. And our catalysis work has mostly been funded by the NSF and the Department of Energy. This is actually, I was going to point out specific people, but my group changes all the time, as those of you who are professors know. And I was thinking that not everyone that did all that work is in this picture right now. So, but they're really, really fantastic. And actually, I always have to add this too, is that the amount of resilience they showed getting the pandemic was amazing, especially my graduate students who had to work in shifts and alone sometimes. It was kind of difficult for them, but they were really amazing at keeping everyone's spirits up. The research would not be done if people didn't pay the students and the postdocs. And for that, the catalysis work is mostly funded by the NSF and the Department of Energy. I really have to give a lot of credit to the Sloan Foundation. I've been wanting to do carbon capture since 2013 when I got to UCI, and no one would fund it. And that was sort of a different time, I think, in our in what we were thinking was important. They funded us several years ago with a large grant that was collaborative, and it really drove that program in my research group. It wouldn't have happened otherwise. And then also the Gleason family, Nathan Gleason is a UCI alumni who's given us various amounts of money to do some high risk ideas, which we probably wouldn't get funded otherwise, including like a CO2 redox flow battery, things like that. So I really appreciate their support. It helps us with the seed funding. I do want to finish on one last note, and I always think about this a lot. This is an article published by an electrochemist, and I just want to read it for you because I think it's very interesting. And he basically says, if our Black and nervous civilization based on coal should be followed by a quieter civilization based on the utilization of solar energy that will not be harmful to progress and human happiness, right? We don't have to give anything up to go to solar. There will spring up industrial colonies without smoke and smokestacks. Forests of glass tubes will extend over the plains. And inside these will take place the photochemical processes that have been the guarded secrets of plants, basically mimicking photosynthesis. And if in a distant future, the supply of coal becomes exhausted, civilization will not be checked because we will continue as long as the sun shines, right? So I love this quote, but one of the things I love about it is that, you know, I wrote here that it was written in September 12. That was in 1912. So 100 years ago, this very early electrochemist, you know, basically had the foresight, and photochemist, actually, he did a lot of different things, had this foresight to think about, you know, if we could just understand how natural photosynthesis works, that we can imagine a future without fossil that would be much cleaner and prosper just as equally. And so I always enjoy thinking back on this, and that this has sort of been a dream for over 100 years, at least by some, that hopefully will become a reality, especially in the last few decades of research. Thank you.
Thank you for that inspiring talk. That was wonderful. And that quote at the end was just fabulous. I'll be thinking about that for a while. We are going to open it up to questions, but before I invite you up here, before I do that, I want to present you with this plaque to commemorate the lecture and your visit to Penn as our second Vagelos
Thank you very
lecture.
much. Wow, that's heavy.
So we can put it back. You don't have to. So if you want to have a seat, we'd love for students to have questions, and Viper students we've heard about how Jenny was inspired in her undergraduate experience. I hope this lecture inspired you, and we'd love to hear some questions from you.
Great talk. Are your catalysts air and water stable, and do they have to be in order to be industrially viable?
So our hydrogen evolution catalyst, we designed to work in water for that specific reason that most organometallic compounds are not stable in water. The problem with anything with oxygen, and we've learned this because we do a lot of reduction chemistry, is oxygen is very easy to reduce. So there's very hard to reduce. I think you can sometimes reduce protons in the presence of oxygen, but it's very hard to do CO2 in the presence of oxygen because it will always reduce first. It's very reactive, right? Oxygen is much more reactive than CO2. Yeah.
We're just going to ask for you, this one in the front, please. We're going to ask for you to hold your question until you get the mic, because there are a lot of people online and they want to be able to hear your question, and they can only do that through the mic.
Hi, I'm just an undergrad, so I'm trying to take mental notes on like how all this research ecosystem works and whatnot. So I wanted to ask, you said you had some troubles getting funded at first regarding carbon capture. I was gonna, like, how did you overcome that? What was your approach? What did you try to show these people? And like, Like, did you need to produce something at first, or like put a tangible goal in front of them?
It's a good question. I'm trying to think of how to answer the first part. The research agenda is set by Congress, which changes and you know, other things a little bit. And so they're just different priorities. I would say that what worked for me with the Sloan Foundation was that, and this is actually true for, you know, early professors, is that foundations like to fund things that are not funded by the federal government. And that was actually the big plus, right? So they actually wanted me to tell them like why I can't just get federal funding for them. And I was like, these are my applications and this is what they've said. You know, it was like, you know, the basic energy people were like, we're not doing this right now, it's too applied. I went to the applied people, like, what you're doing is too fundamental. You know, we sort of went back and forth. I showed them all those responses I got from program managers. I was like, you know, we live in this space right now. We want to do fundamental research on a new way of doing this that is not currently, we cannot get funded for. And they really bought that. And they said that was great. And actually, the grant that we got can sometimes be renewed. And I talked to the program manager because it's, you know, it was expiring. And he says, you can get money from the federal government now to do it. So we're not going to fund you anymore. But it was, I mean, it's what we needed. We needed that seed funding to sort of get going on it to do that. So yeah, but it is often, if you can't get something funded by the federal because they think it's too risky or something, foundations often prefer to live in that space, I think. Yeah.
And we're very lucky at Penn to have, through the Vagelos Institute, where we can provide seed funding for exciting new projects and get the results to go forward for federal funding. So that's, we're very grateful to the Vageloses for that. I think there's another question right here.
I was wondering about the quinone you were showing towards the end. Have you tried different substituents on it other than the chlorines? And like, I mean, I guess you're limited by solubility there, but.
That is a fantastic question. Are you, I will talk more about in my chemistry talk tomorrow, but the quinones tend to have a trade-off between redox potential and their binding ability. So as they become, when they bind better, they tend to be more reducing, which is the problem in the presence of oxygen. And so we had to sort of play tricks to sort of get it to become more oxygen stable without hindering its capture ability. But you're exactly right. I mean, we basically, and not just us, the people who work before us on this, you know, have published a couple dozen of different quinones and their properties, their redox potential and binding properties. Yeah.
I think there's a question here.
I really loved your carbon capture portion of your talk. It looked to me like you were gearing that toward the smokestack application where the CO2 is fairly concentrated. Does this give you some ideas for capturing CO2 either from the oceans or just from the air, or are those totally start from scratch, different projects?
So when we started, we were very like obsessed with flue gas because that was sort of the big application at the time. Since we've been working on it and talking to people, basically the overall energy efficiency is very bad. Like I said, it's about 3%. But one of the reasons why it's less bad is because they use a lot of process heat, which would be wasted otherwise. And they've also sunk a ton of money into amine thermal regeneration. So when I've actually talked to people who work in the industry, they said it's going to take a lot for us to like reverse course and do something different. Plus, right now, electricity is more expensive than waste heat, right? So because of that, we've been, in the last year, really been focused on applications where there's no process heat available, right? So a lot of chemical like steel, concrete, they have some process heat associated with that they can use to capture Haber-Bosch, things like that. Actually, the one that my group thinks I'm weird because I get obsessed about these things, but the one that we've been really into lately is actually coupling with HVAC. Because if you carried a CO2 meter around during the pandemic, you know that the CO2 in this room right now is a lot higher than out there. And we know from thermodynamics that as you go to higher, it gets a little bit easier. And you know, one of the benefits in the Sloan Center is that we got to work with an electrochemical engineer who did a lot of modeling for us. and we started showing us like air handling, there's all these energy costs associated with air handling. And I was like, well, we're doing this anyway in our buildings, right? We're already moving air around. So why don't we just use that, just add on to that energy cost a little bit, and it would be much more efficient. And actually, now I can go on a lot about HVAC for quite a bit. That's what I mean when I get into,
No, that's
but
good.
it actually, and actually, we're not the only ones thinking about this. So I went to an RPE workshop on air capture and HVAC recently, and what was fascinating to me is that I talked to someone from Carrier, which is an HVAC company, and he said that you can capture the CO2 from HVAC and throw away the CO2 and still have a huge negative impact on carbon footprint of a building, because in order to keep CO2 levels down, they have to bring in so much fresh air. And that fresh air has to be heated and cooled and dehumidified if you're in Florida. Florida is like huge, like places like that. And the way that they dehumidify is just very energy inefficient. They cool it down to the dew point and then raise it again to like comfort level. And he said that if you could just skim off the CO2 in an office building so that it would be within standard and people wouldn't be getting dizzy or something at high levels, then you could throw away the CO2 and still have a huge impact by reducing heating and cooling costs. I mean, of course, we don't want to throw away the CO2, but it was just fascinating that would just have such a big impact. So we've been learning a lot about HVAC recently in my group.
That's remarkable.
Yeah.
Thank you. Thanks for sharing that. Are there other questions? Are there questions online, Nadine? Everyone's quiet online. Feel free, if you're online joining us, to put your questions in the chat and we'll ask them. Question over here. Just hold on for a second, because we want to make sure that people online can hear you as well.
Can you hear me?
Yes.
I'm a first year student in Viper, and I thought your talk was very inspiring, especially from someone who's new to the energy research sector. When you talked about recycling CO2 into fuels, you mentioned how like carbon monoxide was very energy rich. I was wondering if you could elaborate on the usages of CO in future energy technology.
I think it would be a precursor to liquid fuels. I think there's work on reducing CO directly into liquid fuels using electrochemistry. But with the Fischer-Tropsch process, which has been known for a long time, you can use it as a precursor to get longer chain hydrocarbons. And effectively, you can get diesel from it. So yeah, so it's definitely, it will be used in a step to get something else. And to be honest, I would rather make liquid fuels directly, but I don't know how to do that. Neither does anyone else. So, I mean, CO in some ways is a lot easier because it's only 2 electrons. So as far as the limits of our chemical knowledge, I think that's where we are. Yeah.
Well, something that you can think about as well is in a lot of the way that nature converts CO2 to essentially liquid fuels. It does it through a series of catalysts. So it's not just one catalyst. It'll take one catalyst, convert it to an intermediate molecule, and then another catalyst will take that down the way. And so a lot of groups are working on getting from CO2 to CO, and then using another catalyst, hopefully electrochemically with solar energy, to get to liquid fuels from there. So CO is more of an intermediate in the production of liquid fuels. Great question.
Yeah.
Hi, thank you for your talk. I'm a postdoc here at UPenn in chemistry, and I have kind of like a general 2-part question. So it seemed like, of course, your talk was very like seamless since you're given it in this kind of forum, but I'm just curious a little bit more about how you came up with each catalyst. And you mentioned having collaborators that ran tests for you and engineers. And so in addition to that, I have a question about who are the types of scientists you have to work with for this? And what do you all need from each other to like really pump this up to like the manufacturing level and things like that?
Those are great questions. The first one is, yeah, science is not seamless. I actually, since I got tenure we've had complete group turnovers in the last year or two. I've been giving talks to my students about how their project started and how many times they didn't work and what we learned from that and how they've evolved over time. And there are some projects in my group actually that came from something that didn't work, but we're like, oh, well, it's interesting for this reason. So that is, I mean, I think actually for the postdocs in my group that are about to start faculty positions, that was, they were just amazed because, you know, I go give the talk, I'm like, oh, look at this, it's so neat. But many times it was many stops and starts and it was like, this didn't work and, you know, unexpected things happen. So that's very common. The collaboration, I love it because I'm not an expert on lots of things that I want to be able to benefit from. So we collaborate with theorists and electrical engineers, spectroscopists, various people. And you know, to me, it's really driven my program a lot further than it would have. If I had never heard about the energy demands of air handling, I would have never gotten to HVAC, which you know, but also not only that, but the engineers also, you know, have given us cost models and different, you know, there were a lot of things that were not intuitive to me. Because I was like, you want the best CO2 binder, you know, that works in air. And they were like, no, actually, because you always have to pay back that energy, the extra energy you have. So you know, and then they gave us these charts that were like, you know, depending on the concentration, you know, these are the, you know, and then it also matters what the cell design looks like. And then they did all that modeling for us. They gave us charts that were graphs to tell us like what we need to target for different applications, different cell designs. So that was super useful. Our computational chemist, you know, there's sort of a joke, and she actually gets very riled about this, is that, you know, computation follows experiment. It's not the case for much of our work. She actually screens ahead of time. And then we validate, and then we learn something, whether the validation is correct or not. So during the pandemic, which is when this project started, one of our postdocs that was, you know, we weren't allowed in the lab. He looked at 80,000 quinones computationally, right? And then we validated it, and then we didn't find the predictions to hold out, but basically we were able to learn why they did it and how we would need to screen them in the future to be a more accurate model, right? So, but then she also has actually also given us a lot of leads that ended up being fruitful as well, right? So in our case, she actually does lead a lot of the research, and we follow with experiment. And then you had another question. Oh, about scaling. Yeah. So the reason why I talk to people in industry is because there is a very naive, I think, but when I first started talking to people in the industry, it is amazing how hard it is to get something from here to like, I mean, I just had no idea. And so I try to talk to people whenever I can, because I just need to know what the problems are, right? There's just things I don't even think about, right? That they tell me, and I actually do want to, you know, make some of this stuff a reality. And so it's been really, really useful to think about all the things that actually matter. And also just to talk to people that know how to scale things, right? There are people who are experts on how to get something from the lab to, you know, and these are the people you need to talk to. Yeah.
Yeah, those are great questions. And I'm sure there are a lot of students in the room who are working on research and things don't go well for a while, and then
Yes.
something clicks, and
Yes.
then you build on other people's work. And so we've all been through that. And the collaboration part, you know, is key. And I hope in the Viper students will have the opportunity to not just work with one research group, but collaborate with other groups and learn from the things that your cohort is doing in other labs as well. Question over here.
I enjoyed your talk very much. I'm wondering if you're willing to project a little bit in the future and speculate, because you see so much, right? And speculate on what the sort of the ultimate resolution to energy storage or carbon, the CO2 problem, what that's going to look like. You know, for example, do you see multiple small solutions, or one major discovery as the other extreme?
I think the problem is big enough that it's got to be a lot of different solutions depending on the application. Before the pandemic, I saw that they were planning on building energy storage into the Hoover Dam for Southern California. I haven't heard about it recently, which makes me think that the project stalled out. But basically doing exactly pumping water uphill during the day and letting it run down through the dam at night. I've heard about literally moving rocks uphill and then having them run down, right? Or compressed air, right? That's another way of mechanically storing energy. There are a lot of different ways of doing this, and I think in the end it'll depend on location and scale for what the solutions are.
Right, well, I think we're nearing the end of our hour here. I want to thank you all for joining us. We want to welcome you to a reception downstairs. So we hope that you'll stay and celebrate this talk with us. And Jenny will be around to answer additional questions and you can discuss things among yourself. Tomorrow, Professor Yang is giving a talk in the chemistry department, which will be much more in-depth about the Science Center Research Group. We welcome you to join us there. That's at noon tomorrow. And there are many other events through Energy Week that you can go online and find that are happening all over campus. So with that, I want to thank you all and let's thank Jenny again. Correct. So please enjoy the treats downstairs.